So we're just going to real quickly walk through this answer and the work behind this. And then we'll talk a little bit about some of the pieces on it. So what are we solving for? Oxygen atoms. Okay, so we could write atoms. Our formula for oxygen is important. We're specifically referring to an oxygen atom. So our formula is just a single oxygen. Okay, not O2. What are we starting with? Moles of oxygen, which in this case is moles of O2. Kind of being nice there, because I could have just written it moles of oxygen. If it was written as moles of oxygen, what is our formula? It's still O2. Okay? It's only when we say oxygen atoms do we know we're only looking at a single oxygen. Okay? So we have to be very, very careful within that. And the numerical value for that was 0.240 moles. Okay? So we now go through and look and say what changed. We've got moles and we have atoms. So our measurement unit has changed. Okay? The other thing to note is that we have O2 versus O. Okay? So our substance unit has also changed. So we're going to have to do two types of conversions. Which conversion do you want to take a swing at? O2. Okay? So what we'll refer to in this case now is our O2, and I want to convert it to oxygen atoms. Okay? Or sorry, just oxygen at this point. What would be the measurement unit in this case? Okay, we can use moles. Where do I find the numerical relationship between the moles of oxygen and the moles of O2? That comes from the chemical formula. So I would look at the chemical formula for O2. In that chemical formula, if I'm given 1 O2, how many O's do I have? 2. So I would say 2 to 1. So I'm just looking at 1 O2. That would be an O2 molecule more than likely. Why am I allowed to drop in moles? What is a mole? Define a mole, because in this case we aren't using mole as a conversion factor. So that mole value there is like saying 6.022 times 10 to the 23rd. Okay. So because they're both moles, I can ignore that 6.022 times 10 to the 23rd factoring in there because I've kept it consistent in both places. Kind of make sense? Okay. Oh, now I got to stepwise all the way back. So I can keep this as moles and moles. What happens to the units? The moles of O2 cancels, and what unit would I now have? Moles of oxygen. Is moles of oxygen the same, or sorry, moles of oxygen atoms, is that the same as atoms of oxygen? No. Okay, that's like saying a dozen eggs is the same as eggs. Okay, no, it's not. 12 eggs is the same as a dozen eggs. So we have to take into consideration now that mole value. We need to get rid of that measurement. Okay, so moles of oxygen atoms can be related to our atoms of oxygen. Where do I find the conversion factor for moles related to atoms? That is our Avogadro's number. And ran out of space there. What numbers get put in here? 1 goes with moles. So I put the 1 there. 6.022 times 10 to the 23rd goes with atoms. Okay, what happens? The moles of O cancel. What would I have as an answer? Atoms of oxygen. This one becomes a relatively straightforward one to calculate because everything's in the numerator. All I have are 1s in the denominator, so I can just punch it into the calculator and get an answer. Okay. Does anybody actually want to calculate that? Okay, it's not that big a deal to me personally because the work sets that up. The next part is entering it into the calculator, and this one I would think is straightforward. We will do ones where it's not as straightforward entering it into the calculator. Those probably make more sense to calculate out. This one will 7 times 10 to the 22nd. Ish. I may just made that up.
I had 2.89 times 10 to the 23rd.
Whatever.
Right.
I didn't have a calculator. Give me a break. What was the number? 2.89.
Yeah, 2.89.
10 to the 23rd. One thing to consider here, since we're looking at atoms, are atoms really, really, really small? Yeah, so if I have atoms, and if I'm going to look at the number of atoms, more than likely the number of atoms I would be looking at should be really big. Why? Can I measure an atom? No. So typically, when we're thinking about atoms, we should be looking at a very large number of atoms. We most certainly should not be looking at a 10 to the negative. Why not 10 to the negative? That's less than 1. I can't have less than 1 atom. Does that make sense? So that can be a quick check when you run your calculations. If you say you're solving for atoms, but all of a sudden you've got a power of 10 that's a negative, that doesn't make any sense. You screwed up your calculation. Make sense?
How did they come up with the 6.022? Like
How did we come up with that number? That might have been left in the play posit. I'm not sure I've got a slide specifically on that. The reason why we picked a mole as 6.022 times 10 to the 23rd ultimately comes from how we would go through and do these conversions. If I wanted to measure out, let's see if I can quickly come, I can't. It's ultimately the relationship between grams and AMUs. Right? It's trying to help out with our periodic table so that when we look for the molar mass of something, okay, the mass per mole, so we have a conversion factor. If we look at the conversion between grams and AMUs, it's 1.661. Okay, we'll just say 1.61 times 10 to the negative 24th. Grams is 1 AMU. Okay? So what this is now saying, whoops, if I wanted to measure out the mass of a single atom of oxygen. Let's see if I can do this right. If I look at the periodic table, the mass of a single oxygen would be 16.00 AMUs. This is all oxygen now, so I'm going to skip the substance unit, mainly because I ran out of space. All right? So these AMUs would cancel, and this would get me what for a mass? Big number, small number? Small number. This gets you on the order of 10 to the negative 23rd. Your balance only goes out to 10 to the negative 3rd. Okay? So you're off by 20 powers. Okay? To be able to get a balance that weighs that accurately, to measure out a single atom of oxygen, is so insanely small, I can't do it. Right? So instead, what we went through and did is said, well, how could I scale up the amount of oxygens that I could get a measurable mass? So what should I scale up by? And that's really what the whole Avogadro's number is about. Okay? So I want to get the gram value at the end of this to be measurable. That says measurable. Okay? So on the order of at least 0.001, because that's what our balances go, that's the last precision of our balance. That's not really all that precise. So ideally, if we go through and measure this, we're hoping for something on the order up in this range, because now we can get some sig figs associated with that. Okay? So what we're now going through and doing is saying, is I'm not going to measure a single atom. I'm going to measure, because this is AMUs per atom. Okay? That's 16 mass units for one atom. I don't want to measure a single atom anymore, because that's now a value that is too small. So I'm going to scale this up. Okay? And in that scale up, I'm going to invent is the word, a new conversion. Okay? So it could be dozens of atoms. Okay? We already have dozens, so let's do that. So one atom, 12 atoms is 1 dozen of atoms. Okay? That scales me up a little bit, but does that get rid of this power of negative 24? No. Right? I'd still not be anywhere near that measurable value. Right? So that's not helpful. So I could say 1,000 atoms. Okay? That gets rid of a few more zeros. Okay? But again, the order that I'm trying to get rid of is pretty much cancel out that value. I don't want 10 to the negative 24. At best, I want 10 to the negative 1. Right? So my goal is to get rid of that entirely, 10 to the negative 24. Right? So let's just go through and say that my new unit down here for moles, because it's a new conversion, so I can't call it dozens anymore. I'm going to call it moles, and I'm going to define my moles to be 10 to the positive 24. Why positive 24? So that it would cancel out the 10 to the negative 24, right? That would be useful. So if we went through and did this calculation here, we'd have 16 times 1.61. Okay? And we now get a mass that was measurable. Okay? As a ballpark, what are we looking at? Roughly 24. So I'd be getting 24 grams in 1 mole. Ballpark. Okay? That's now reasonable. I can measure 24 grams. That gets me into the right range. Okay? Why do I not like this conversion? Okay, well, to get there, I had to do these 2 conversion steps. Ideally, the system or the number I want to pick for moles means that I don't have to do this conversion. That the number I get at the end should be exactly what's on the periodic table. Because if it's that, I'm done. It solves everything right away. Okay? So I want something that would entirely cancel out this term. So if that term becomes entirely canceled, what would happen? Okay? When I multiplied those 2 things, they become 1. My answer becomes 16 grams per mole. The periodic table would now tell me a mass per mole explicitly. I don't have to do any mass conversion. It's there. That's the power of this. So what number would allow me to do that? Okay, so again, what I'm trying to do is entirely cancel this number out. Okay, so what could I multiply by to cancel that number entirely? What would I multiply 2 by to cancel 2? 2 times 2 is 4, so don't multiply by 2. What would I multiply 2 by to cancel it out? 1/2. So now 2 times a half would be 1. So the term cancels. I don't have to worry about the math. Okay? So what would I need to multiply by to do this? The inverse of this number. Right? So we take 1 divided by 1.61 times 10 to the minus 24. Right? That would be an awesome number to pick, because then I don't have to worry about these conversions anymore. Anybody got a calculator? Some of you do. Take 1 divided by 1.61 times 10 to the minus 24. See if I actually got that number right.
It's 1.6605.
Damn it. For the record, I did say 1.61 or 1.661. So I did say that.
1.66.
So let's do that. Take 1 divided by 1.661. Again, keep the 10 to the negative 24 in the denominator. What do you get?
6.02 times 10 to the 23rd.
So the perfect number to cancel out that mass conversion was 6.02 times 10 to the 23rd. That would perfectly cancel out. That would be an awesome conversion, right? Because then I don't have to worry about that mass conversion. It immediately, the periodic table immediately tells me, whoops, let's fix that 24, that instead of looking at the mass per atom, I can now look at the mass, we just said oxygen atoms, for mole. And that's fantastic because now I have a measurable value. Right? So that's a pretty cool number to pick because it cancels out that mass conversion. Sorry, pointed wrong spot. That is Avogadro's number. We picked that number because it gets rid of our gram to AMU conversion. That's why we picked it. Right? So there's a really solid fundamental behind it. It's not just some arbitrary random number we picked out of thin air. It was to cancel the gram to AMU conversion. And by doing so, we've now taken the periodic table that could only measure atoms and AMUs for that matter. I don't even have a balance that measures AMUs. And it takes that unit and it moves it up to a unit that is now measurable and I can use in labs. So this means when I go into labs, I'm not measuring the number of atoms. I'm measuring moles of atoms. And I have to measure moles of atoms because I need a measurable amount. A mole of atom gets me up to grams that I can now use. Right? That's the beauty of Avogadro's number. Right? So it pretty much takes our periodic table with mass units that were useless and now makes all those atomic weights useful. Because now when I look at the mass for, let's say, helium, it's no longer 4 AMUs, it's 4 grams per mole. I now have a unit or a measurement that I can work with, that I can measure in the lab. It's just a scalar factor. That scalar factor is phenomenally cool because now I don't have to do all this extra unit conversion. Right? And this is where I kind of differ, I think, from some other chemists. Avogadro's number is phenomenally neat because it does that. Does that mean I need to use Avogadro's number?
You don't need
That's it. It means exactly that I don't need to use Avogadro's number. Right? The only reason I would use it if I'm trying to deal with atoms. Right? Rarely, if ever, do we deal with atoms. We just don't deal on that scale. So when do you have to worry about Avogadro's number? Chapter 8, when we're specifically talking about converting atoms into moles. And the whole point behind all of those conversions on using Avogadro's number is to see that we can scale things up to a point where we can measure them. But once you've done that, that's all you need moles for. Ta-da, I'm there. Right? And I don't have to worry about it. It makes sure that all of the equation stuff that we use, it makes sure that all the math stuff that we use is now all scaled up and useful for everything. So when I look at a chemical equation, I'm no longer looking at molecule plus molecule to give me more molecules. I'm looking at moles of molecules plus moles of molecules to give me moles of molecules. And because everything scales up by that exact same factor, it's a perfect relationship. Right? And if I use different ones, well then everything hits the fan and it becomes miserable. More miserable. Because you don't look all that excited. Kind of makes sense? Okay. This is a good question, because it's weird. Why would you pick that? Okay, so let's try the next big thing, which is right here. So we just covered that. That means our atomic mass becomes the molar mass. Okay? So when we look at the mass on our periodic table, which is the number underneath the elements on our periodic table, we now can refer to that as the molar mass as opposed to atomic mass, and that is pretty insanely useful. Okay? We can now reference that as a molar mass, molar being moles, mass being grams. Unfortunately, the word's a little bit weird, because if we looked up the molar mass of helium, what would our units be? So if it's molar mass, we would say 4, I'm going to do sig figs, grams per mole. So when we say molar mass, we might say, well, wasn't it 4 moles per gram, because we say molar first? Sorry. Okay, so it might be better to remember it as the mass molar. Okay. Your number is next to the gram unit. Okay? Kind of makes sense? Ish. So, what is the molar mass for copper 2 nitrite? Okay. Should we make this a little bit more difficult? Yeah, I agree. Looking like you guys are doing pretty well with this. What makes this question harder than what it was initially shown as? Nitrite, which could be the number one thing. The only reason that is harder is
It's not nitrate.
it's not nitrate. You were told to memorize nitrate. You weren't told to memorize nitrite. So I saw plenty of people going back to your notes to look up what nitrite was. That's good. You should do that, because I don't expect you to have that memorized. Okay, so we would have to look that up, and nitrite is NO2 with a -1 charge. I notice that people still like writing the charge up top. I understand what you're trying to do. Okay, so we're going to show this 2 different ways just to make sure you're aware of why I see complications with that. The copper, what's its charge? A +2. Is my formula balanced? No, what do I need? I need another nitrite. Okay, and that would be my formula. If we go through with some of the work that I've seen other people do, it's not that it's necessarily wrong, but I want you to be careful with it. You're writing the charges up, which is fantastic. You are specifying the charges, and you're placing those charges in the proper location in the upper right-hand corner. The proper location for it to be just nitrite and copper ion. However, is this just copper ion and nitrite? No. So if you go through and now say, well, I need 2 nitrites, that answer is wrong. Right? And but isn't that the same thing? Depending on who you talk to, no. And depending on how picky a grader gets, no. Okay? Because by doing that, you're now saying the copper is separate from the nitrite. How do I know they're separate? I have 2 different charges. Okay? So I've implied a plus sign in between. So if you want to show that as work, I admit I will accept credit for that, and I don't think anywhere in your exams would you ever get tested on that as a show your work kind of thing, but it could happen in other classes. If you do that as work, you should also go through and say that this is your official answer. Does that make sense? Whereas when I set it up on the right-hand side, by putting the charge underneath, I'm separating that from it, which means when I figure out my work, my answer is immediately there. I don't have to write it twice. Does that make sense? Okay. Simple, subtle thing, but I want you to be aware of it in case it comes back and bites you at some point later in your chemistry career or in another class. Maybe you had to retake it. Hopefully you don't have to retake it. Okay? So, what are we doing? Molar mass. Where do we find the molar mass? Periodic table. Okay. Is copper 2 nitrite on the periodic table? No. What is on the periodic table? Nitrogen I know is,
14.5.
oxygen I know is, oh, yeah, I should do it. So all I have to do is add those up and I get my answer.
What do you got 2 by the end of 2? Got 2.
I have to realize that I don't have just a single nitrogen, I have 2 nitrogens. So I have to remember that that subscript applies, to what's in the parentheses, so I get 2 nitrogens. So I have to multiply that by 2. I also have to realize, how many oxygens do I have? I have the 2 and the 2, 4. Now I can add it all up and get whatever that answer is. 155, 57 grams per mole. Officially, we should be writing the copper 2 nitride in there, so we'll slide that in nice and messily. You know, the happy little tree. Okay?
Why the tree?
Why
Inside joke. Other questions on that?
happy little trees? Happy little S.
So we good with that? So we just did that. Oh wait, no we didn't.
So now there's more.
Oh, there's more. Yeah. So what is the mass in grams of 0.532 moles of copper 2 nitride? This now scales up. Okay, now I'm not looking for a molar mass. The molar mass, all I gotta do is add up and use the periodic table. Here I'm asking for the mass in grams. Okay, so I want grams of copper nitrite. Except this time I'm not saying the grams per mole. I'm not saying 1 mole. I'm saying, I had to write the unit first. I'm saying 0.532 moles. Okay? So we're now going back to a conversion factor. I have to now be able to convert. So that molar mass one, we don't have any conversion factors. It's just recognizing the formula and the power of the periodic table. Yes?
Can we go back to the molar mass because
Probably
I'm getting
not.
a different number.
Can we get a... So we're going to end up having to use it again here. Okay, so we'll sort of cover that. Okay. We get moles copper nitrite on the denominator. Why do I want it in the denominator? I want to cancel it. What do I want in the numerator? Half right. Thank you. Okay. Where would we get that conversion factor? I'll accept 2 answers. The best answer is from the periodic table. Okay. The next best answer, you just solved it. Okay. So we got one number saying 155. Oh, you got it fixed?
Yeah, I got it.
Okay, 155.57, 1 mole. Now what do? We can multiply it out because the moles cancel and I'd be left with grams of copper nitride. Make sense? Do you see Avogadro's number? No. Kind of disappears from the salt. We could bring it in if we used AMUs for our molar mass. And it would suck. It adds a bunch of extra steps. Right? That's the beauty of a mole. We don't have to do those. Kind of make sense? We're doing well? Okay. So, what is the mass in grams of 2.55 times 10 to the 23rd atoms of lead? Okay. 2 approaches to solving this. Okay, so we'll start in red and then we'll jump to blue. Okay. I'm going to show you the way that you are expected to solve it, but you don't necessarily have to solve it this way. Okay. So we would go through and say, okay, atoms of lead needs to cancel. And what do I want? What do I want? What do I want? What do I, What do I want? I want grams of lead. That's exactly what I want. So I would write grams of lead. For those of you erasing, stop. Do I have that conversion factor? No. So, now I can erase it because I don't have that conversion factor. It doesn't exist. Okay? So, what can I convert the atoms of lead to? Okay. What you are expected to do would be to convert to moles of lead. Okay? Where's the conversion factor between atoms and moles? That is Avogadro's number, which is 6.022 times 10 to the 23rd doesn't mean anything to me. Okay, 1 mole of Pb was the 6.022 times 10 to the 23rd atoms of lead. Okay, so our atoms of lead would cancel. Fantastic. Do I have my answer? No, I need another conversion factor. In that conversion factor, moles of lead needs to cancel, and what do I want?
Grams.
I want the grams of lead. Okay, this was memory. Is that how you spell memory? Yeah? Okay. I'll trust you. That's not how you spell memory. Is it? Okay, the next one. The next one comes from the periodic table. Okay, and in that we know that 207.2 grams is 1 mole of lead. We can now punch into our calculator and we get an answer. We'll deal with that calculator in a second. Let's go to the other way to do this. Okay. Again, I'd want atoms of lead into grams of lead. I don't have that conversion factor. Is there another conversion factor for atoms into something else? AMUs. Where do I find the conversion factor between AMUs and atoms? That's on the periodic table. Okay. Where 207.2 AMUs is 1 atom of lead. Okay. The periodic table holds both of those unit sets in it. That was the power of Avogadro's number. Okay. Is that we could interconvert those. The problem with this is AMUs grams. And so what do you have to do? You have to convert to grams of lead from AMUs of lead. Where do you find that conversion factor? Okay. I gave it to you on the front of the exam. It's actually there. 1.661 times 10 to the negative 24th grams is 1 AMU. I've done this conversion a few times, that's why I've got that memorized. Well, almost memorized, because I screwed it up earlier. Thank you, Mike. All right.
That's where you say.
Now we could go through and solve. Okay? Both of these are going to result in the exact same answer. It's going to come down to what you recognize first and allows you to move through it. Okay? Arguably, the blue one is less effort on your part because where did that conversion come from? That second one. Okay? It's given on the exam. Okay? So you didn't have to memorize Avogadro's number. Okay? You're going to have to. Like, you should do it. Okay? You should memorize Avogadro's number. It's kind of important. You do need to know that. Okay? But I am giving you an out. I'll still allowing you to go through and solve. Okay? Kind of makes sense? Okay. The bottom calculation might be easier to enter into the calculator because where are all your numbers? In the numerator, so you should be able to multiply that through and it not be a big deal. The top one becomes a little bit harder because one of your numbers is in the denominator. Okay? So when you go through to enter this, and I'm going to erase the bottom one. Okay. There's a couple approaches, erase, thank you, that you could go through and do. So 2 point, I already got the number, 55 times 10 to the 23rd, parentheses, divided by, is that what they show as divided by? They probably do the little division symbol. Division symbol, 6.022 times 10 to the 23rd. Here's where you run into a problem. Entered like that, where's the 10 to the 23rd? That's now in the numerator. I don't want it in the numerator. That's part of the denominator, parentheses. Okay? Times 207.2.
So you can't times that first one to the...
So that is how you could enter it, just streamlined right away. My argument should be that you would do 2.55 times 10 to the 23rd times 207.2. Okay. What is it? 6.022 times 10 to the 23rd. Get whatever that answer was on top up here, number, and then divide by your 6.022 times 10 to the 23rd. Even in that division, what are you going to need? You still need parentheses to make sure that that 10 to the 23rd shows up in the denominator. Make sense? Okay. Fortunately, it's part of the class. You have to know how to use your calculator for these. Questions about that?
I have a comment. Couldn't you just technically cancel out the 6 to the, or 10 to the 23rd would be like 10 to the 23rd?
So, are there mathematical simplifications that you could do if you were mathematically inclined? Absolutely. And arguably, I would have done that too. I just didn't see it right away. This 10 to the 23rd is in the numerator. This 10 to the 23rd is in the denominator, which means I can cancel them out right away. I don't have to worry about the powers of 10 at all. Okay? That is an extra step. You have to be comfortable with that mathematics. If you aren't, don't do it. Okay? Make sense? Just as kind of a sort of thing, that canceling the powers of 10, if you have to move on, if your goal is med school, dental school, pharmacy, engineering, you need to be comfortable or start to get comfortable with canceling out your powers of 10, because they're going to make you start to do calculations that you have to approximate. You can't use a calculator for. Okay? So, now's not a bad time to get comfortable with it. The exam, you might still write it all out and don't do shortcuts, because shortcuts can lead to errors, particularly if you aren't comfortable with it. Okay? Make sense? Everybody good? Okay, you guys want to do another one? I got a yes and a no. Sorry, the yays win, or yeses win. What is the mass in grams of a single molecule of sulfur dioxide? I'm going to help you out here and say the molar mass of sulfur dioxide is 64.07 grams per mole. One question kind of popped up that said, well, couldn't you do this with a formula? The formula is how you could solve it. Yes, absolutely. There is a formula for everything out there. Ultimately, what a formula is an algorithm to solve a question. Which question? That specific question. The problem with that process is you will get asked different questions, which then means if you've memorized a formula to answer one question, as soon as the question's changed, what do you have to do? Memorize a new formula, and a new formula, and a new formula, and a new formula. Okay? You're going to end up memorizing way too many formulas. If you can do it, that's awesome. That's fantastic. I can't. Okay? What I want you to do is recognize a process that always works. Because again, right here, we're actually doing very simple conversions. It's when we move up to equations where you now have to string together 3 or 4 conversions. That's a complicated formula to memorize. Okay? And if you haven't spent the time to figure out the process with the easy stuff, you won't have a process for the harder stuff, and you'll have to try and come up with a new formula. Okay? So again, the process is what drives this. Okay? I cannot stress that enough. Okay? So, what do we want? We want grams of sulfur dioxide. When do we want it? Just checking. 1 molecules. It's a bit silly to pluralize it, but whatever. Sulfur dioxide. We don't want molecules. Of sulfur dioxide. Ideally, I want grams of sulfur dioxide. Does that conversion factor exist? Okay. No. And that is one of the hard questions in this section. Okay. You have to be thinking about where these conversion factors are coming from. That's what makes this next unit more challenging. Okay. Instead of being like, oh, I just looked that up. Okay. It's, well, can I look that up? Okay. You have to be able to answer that question. That ultimately comes with practice. Sometimes you'll be like, I don't know. Then you're stuck. Okay? You're dead in the water. There's anything you can do. Move on. Okay? Or try a different tact. Okay? So what could I convert molecules of sulfur dioxide to? Okay? We could convert to AMUs. Okay? Arguably, I don't want you going to AMUs because the whole point is that we're supposed to memorize Avogadro's number with moles. Okay? So I'm going to avoid the AMU one from now on. It works. Okay? So if you want to use the AMU conversion, you can, but moles is one of those big things that everybody's supposed to know, so I kind of got to press that a little bit. What's our conversion factor? Where do the numbers then go? Okay? And this is one of the challenging things with this. You go, oh, well, that's Avogadro's number. That's fantastic. Okay, I know that that says Avogadro, and Avogadro's number was 6.022 times 10 to the 23rd. No, that is not Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd items or things. A mole is a grouping of things, which means you've placed the number in the wrong spot. Okay? Which goes back to knowing the unit. The numbers themselves are meaningless until you attach a unit to them. So you have to know the unit to be able to match the number. Okay? What unit would we now have? Moles. Do I want moles?
No.
Nope. So moles of SO2 needs to go on the bottom, so it cancels. What do I want on top? Grams of SO2. Am I given that? Yep. Where am I given that? In the question. Give me another answer. Periodic table. So depending on what's being tested, you may be given that information or you may be expected to look at the periodic table. Okay, it really just depends on the level. So because it was given to you, what are you being tested on?
The computer process.
You're being tested on, do you know Avogadro's relationship? Okay, or the AMU relationship to be able to do that conversion. Okay? Kind of make sense? Yeah? Okay. You want to do another one? Okay. The no got kind of loud there, so we'll let the no win on that one. Okay. So I would recommend. So I will go back and point at this. You should go through this question, solve it out, make sure you understand it. One of the key things to watch out for in this case. What are you solving? Sorry, what are you solving for? Fluorine atoms, which is F. Fluorine gas is F2. You do got to watch out for your nomenclature systems behind how you solve these. Okay, it can bite you. This question, unfortunately, if you screw it up twice, you get the right answer. Yeah, you have to screw it up. If you screw it up twice, you get the right answer. So it's kind of a bad question because if you screw it up once, you almost always screw it up the second time also, and you end up getting the right answer. So it's a bad question in that respect because you're getting credit for doing it wrong. Okay, so just be aware of that. Which really shuttles us into Chapter 9. Okay, Chapter 9's biggest deal is that you're looking at a chemical equation. Right? A chemical equation is a recipe on how you go through and make something. Okay? And it gets very specific, and we have to follow those specifics. You can't vary it, okay, or start to change it in between. One of the big things that changes with the chemical equation is if I say give you chocolate chip cookies, that was going to be the wrong thing. What did you use to make them? Chocolate chips. Well, you know that because you've made chocolate chip cookies or you recognize the pieces within it. Okay? You're using a chemical equation to make those cookies. Okay? The same thing is happening up here. You're converting chocolate chips into chocolate chip cookies. Okay? The substance changes. Same thing is happening with your chemical equations. We're converting a substance from one phase or one system, unit system, to another, which means we absolutely care in our unit to specify the substance. Okay? And everything we just solved, we always included the substance up to this point, and it really wasn't that important. And it wasn't important because the substance never changed. As soon as you do a chemical equation, what happens to your substance? It changes. So we have to be very, very cognizant of the substance and make sure it's included in your complete unit. Make sense? Okay. So, equation usage. Provide simple instructions on how to build a bicycle. How would you do it?
On how to build it.
Yep.
How would be simple.
I'll give you some context. Assuming there are just wheels and a frame.
You assemble the wheels of the frame.
Just wheels to the frame. So I take my wheel
You assemble it to the frame using.
and I take my frame and now I have a bicycle. Oh, I need 2 wheels. Okay. This is a chemical equation. I'm specifying the amount of each of those pieces that needs to go in to make the final product. Okay. Your chemical equations are doing the exact same thing. It becomes harder with chemical equations because why is it harder to understand? You can't hold these things. You don't have that tactile initiation to be able to say, I understand what's going on. So we have to kind of use our imagination to extrapolate out and make these things big pieces and say, well, these big pieces are doing this. Okay? Just like a bicycle. Okay? So we could draw it out as 2 wheels, but like we said, we could come up with abbreviations, and we get 2 wheels and a frame. Okay? Don't get nasty on the details. Okay. Someone built 4 bicycles, or 4 bikes. How many wheels and frames were used?
8 wheels.
How'd you do that?
There's 4 of the 2.
Parentheses around everything and 4 outside.
You need 4 pairs of wheels and 4 frames.
You did 2 calculations. Okay. I had 4 bikes. I need to convert those into wheels. Bikes as a unit needs to disappear. What do I need on top? Wheels. What's the relationship? 2 wheels is 1 bike. Okay. Which means how many wheels did I need? 8 wheels. How many frames? I have to do the exact same thing. 4 bikes, frames, 1-to-1 this time, and I need 4 frames. Okay? You did that, and you did a phenomenal job at that. Okay? Because you're used to doing it. Did anybody actually write down that work before you started this? So this would be my opportunity to be like, what the F? Write down your process. You need to be recognizing the process when you can do it with easy things. Because as soon as we make it more complicated, it becomes challenging to answer. Okay? So always think back to that process and writing it out. Okay? So let's try another question. Given 6 wheels and 3 frames, how many bikes can be made? I kind of liked the longer pause there, but I didn't see anybody's pencils moving. So it looks to me like you did it all in your head again.
No?
Right? Which is okay, but you're getting the idea behind how you manipulate these, right? 2 wheels, how many bikes can be made?
2 unicycles.
Why can't we build a bike? There's no frame. Okay? And this question is here because it's a bit challenging. Almost always when we ask questions in chemistry about reactions, we might say, given just X grams of this, or given X grams of this, how much product can be made? Right? And the same kind of question. And we make the assumption in that statement that it's not just two wheels, right? That we make a minor tweak to this given information. We go through and say, given two wheels, how many bikes can be made? Well, as a chemist, we go through and say 1. I'm making an assumption about that given information. What is that assumption? That I'm also given enough frames. Is that a horrible assumption?
No.
That's a pretty horrible assumption. We really shouldn't be making that assumption. However, that is very often how we phrase it in chemistry. So I want you to be aware of that kind of context. All right? 3 frames, or 3 wheels and 2 frames, how many bikes can be made? How'd you get just 1? We run out of wheels. So what this is starting to address is that when we look at the pieces, we have to see how both of those pieces weigh out. And we're running 2 separate calculations again. Okay? If I go through and set this up, 2 frames, that says frames. 1 frame, that also says frame. 1 bike gets me 2 bikes. Why'd you not say 2 bikes? Because that says 2 bikes. Okay? We have a second calculation to run. What's that second calculation? 3 wheels. I'm going to start abbreviating. That would be 2 wheels you need to make 1 bike. And what do we get? 1.5. Can I get half of a bike? No. Which means, how many bikes could I possibly make? 1. Okay? Even though the other one says 2. How many people would say I make 3 bikes? Isn't 2 plus 1? No, it didn't work like that, right? It's whatever we ran out of. So in this case, we could reference the wheels as the limiting reagent, or a limiting piece behind this. And we have frames in excess of what we need. Okay? 40 grams of wheels and 15 pounds of frames. How many bikes can I make?
7.
We don't know the weight of the room or the weight of the
Okay? This is a super common question that shows up on most chemical equations. And people start going through and saying, well, 40 grams of wheels means I could make 20 bikes. Because it's a 2-to-1 ratio, right? 2-to-1 ratio of what? Units. The number of wheels. How many numbers of wheels are in 40 grams? If you don't know the mass to wheel conversion, you can't do this question. Right? This question forces you to do another conversion. You have to be able to say, if we just look at the wheels, 40 grams of wheels, well, that says wheels. I actually spelled weeds, yeah. Grams of wheels becomes units of wheels. I need that conversion. Once I have the units of wheels, what can I now do? I can do the next step of the conversion. 1 bike is 2 wheels. That conversion factor is something I need. In chemistry, where do we find that information? That's the periodic table. Okay? Kind of makes sense? Yeah, we'll go ahead and stop there.